All right, today we are doing a real deep cut, something for the pro broadcast engineers out there.
Yeah, we're going way past typical streaming protocols. This is pure, uncompressed, live video.
Exactly. Our mission today is to figure out how you take something like ultra high definition, 4K or even 8K, and just hurl it across a massive physical distance with absolutely no issues.
And that brings us to the hardware we're dissecting, the Thor Broadcast F-12G-SDI transmitter receiver kit.
So this is the critical link in the chain for a big live production.
It's the absolute critical link. Think about the problem it solves. You're at a huge stadium concert, an international sports event.
Okay.
You have a signal coming off that camera that's like a fire hose of data. How do you move that fire hose, say, 20 kilometers without slowing it down or degrading the image at all?
And this kit is the bridge from the copper SDI world at the camera to the long-range fiber world.
Precisely. And the core promise it makes is absolute. We're talking zero delay and completely transparent loss-free transmission.
Transparent, meaning the image you see in the control room is digitally identical to what the camera sensor captured.
Identical. Not a single bit out of place.
Okay, so let's drill down into the performance. The whole architecture is built on 12G SDI. For the teams using this, why was that such a game changer?
It's all about bandwidth simplification. It's a huge deal. Before 12G, if you wanted to run high frame rate 4K, like 2160p 30, you're literally ganging multiple tables together.
So a mess of cables for just one camera feed.
A total mess. 12G gives you all that capacity over a single cable. Just cleans up the whole workflow, makes it more reliable.
So that's the data pipe. But moving the data is the real magic trick here. Inside the transmitter and the receiver, we've got these things called reclockers and cable equalizers. What are they actually doing?
Think of them as dedicated signal janitors. The cable equalizer cleans up any noise or degradation from the copper SDI cable itself. And then the reclocker meticulously rebuilds the timing of the digital signal. It ensures every single bit arrives exactly when it's supposed to, right before it even hits the fiber.
And this isn't for short hops. The specs say it uses single-mode fiber for, what, a 20-kilometer-long haul?
20 kilometers. It's seriously robust.
But I have to ask, if you're converting the signal from electrical to optical and back again, doesn't that conversion add some kind of delay? How can they really claim zero delay?
That's a great question. And it's a crucial one. They achieve it by avoiding any complex processing. There's no compression, no encoding algorithms. Those are the things that cause latency. This conversion is basically happening at the speed of light. Its job is to transport the signal, not to process it.
And even the physical connectors are beefed up. The BNC interface has 15 kV of electrostatic protection. This is definitely not the gear you buy at a big box store.
Absolutely not. And when you look at the operational requirements, the endurance is just extraordinary. It had a working temperature range from negative 40 degrees Celsius all the way up to plus 85.
Wow. So you could have this thing sitting next to a camera in the Sahara one week and on a freezing Olympic ski run the next.
And it would just work. It's built for those severe field conditions.
And to guarantee that level of quality, it obviously has to be compliant with industry standards.
Right. It meets all the major SMPTE standards, 424M, 2081, 2082. That's your guarantee that the signal is going to be accepted by any major broadcast network on the planet.
To do that, it has to pass something called the SDI pathological code test. What does that even entail?
It's a stress test, basically. They feed the equipment the most difficult, most repetitive data patterns imaginable.
The worst case scenario.
Exactly. Patterns that can cause clock recovery to fail in lesser gear. What's cool is the internal reclocking is smart. It's engineered to lock onto and perfect only those specific high rates needed for 4K and 8K.
So when you put it all together, what does this mean for the person actually using it? You have this tiny tool, you could hold it in your palm, that uses very little power.
Only about 3.6 watts for the transmitter, yeah. For a camera op trying to keep their rig light, that's huge.
So it defines this space of professional video transport by combining that massive bandwidth with just, well, serious physical resilience.
It does. And that brings up a final thought, something for you to mull over.
Okay.
The technical specs get into these incredibly granular jitter measurements. For instance, the 12G SDI timing jitter has to be less than 0.6 UI. A UI, a unit interval, is essentially the duration of a single bit.
So we're talking about microscopic levels of timing precision.
Microscopic. And that's not just for the picture, it's for the embedded audio too, which has to stay perfectly synced. So here's a question. What does the necessity of engineering synchronization down to less than a single bit's duration tell us about the absolute physical limits of reliably transferring live, high-fidelity 4K or 8K data? That pursuit of flawless timing, that's the hidden genius of broadcast engineering.